Great. So we're going. So today, last week of classes, Monday, Wednesday, today we'll talk about what's on the exam, what to study for that. We'll look at an example from an article by Tony Richardson and Melissa Vanderkay that appeared in 2011 in a journal of Physiology and Behavior. And in that they describe a study that they conducted here at St. Michael's, and then they look at some of the data from it, part of it, and examples of doing t-tests, test proportions, of ANOVA, maybe a regression. So they all can kind of fit in with it in that. We won't look at everything that they do, but it will be kind of an example of how our methods can come into play in those. And basically some time for questions, or ask questions as we go along. I posted some study problems just this morning, so there's some things that from problems from exams in the past. One thing that's not on there is any questions about the control charts. I haven't asked those on exams before, but I'm sure we'll find some way to include those in one form or another. So looking at the homework would be a good guide to the type of things that would be asked on that. So in terms of what's on the exam, we've come a long way. We have a bit of summary. We talked some about describing data, get our quantitative or categorical data, and how would you summarize it, how do you make some graph from it. We talked a little bit about research design and the role of randomization, and how random selection or random assignment to treatments can create data that is useful for answering certain questions. We did some with probability, calculating elementary probability, some with conditional probability, a little bit of reasoning about probability of different events. Okay. And then we spent a large chunk of time here in the second half of the course on statistical inference procedures. And so all together, these things all working together really enable people to do important scientific studies, work on engineering research projects, and generally, figure out things about the world. So the exam is weighted more heavily toward the end, where we've spent more time recently. Analysis of variance was covered on homework 9, one way ANOVA. Given a table of analysis of variance table, how would you decide if something is statistically significant? How would you estimate the variance in the model, and then turn that into confidence intervals for some means? So ANOVA, we've looked some at regression, which is really the homework 10. We'll say a little bit more details about these different things. And then we did some hypothesis testing and confidence intervals. So for hypothesis tests, what we did not have on a previous exam was a hypothesis test related to two proportions. This was really looked at on homework 8. There's a topic there. And we've not had a confidence interval just for a single mean on an exam. This was somewhat on homework 7. In matched pairs, it was there on homework 8. We had two variables that took a difference. you ended up essentially with one variable. So that kind of showed up there. That something on quality control. And normal probabilities. Normal probability calculations. So one part of this, like, is putting something kind of together for a thing. So you got some data, say xi's that are normal with some mean and some variance. What does the distribution of x bar look like? You're taking an independent sample. You're going to take the average of those. Well, the independent sample is normal mu sigma squared over n. On exam 2, there was a problem. Exam 2, number 4. There was a couple things on homeworks 5 and 6 that did some calculations with the normal, calculating normal tail areas or normal probabilities. What's the chance that a value of xi or of x bar is less than some cutoff value? The quality control mostly is graphical in terms of how we're using it. Like if you've got a plot that got lower limits and upper limits, right? And if it veers out of, what does that signal to you?
I kind of unrelated to this specifically, but when exactly is the exam? I just want to make sure.
Oh,
Monday.
Monday. Yeah. So
Monday at when?
At 1 p.m. 1
Yep,
p.m.
yep. So the registrar says, oh, that's
Thank you.
yeah, Monday at 1. I didn't write it, but yeah, whatever the registrar.
I just want to make sure
Monday
it
at
was
1, yeah.
verified with you because I know I could look it up online.
Yeah,
I
yeah.
don't want,
So
I
we're
don't want
gonna-
to be like, well, this is what I thought it said.
Right,
It's
yeah.
the exam.
Yeah, we're going to stay with that same
Okay.
same schedule. Yeah. So in fact, if you look, let's see, Monday, May 6th, 9, is it?
Oh, is it
1 o'clock?
9?
Huh?
I thought it was 9 a.m.
I think it's 9 a.m. Monday, May 6th, 9 a.m.
9 a.m.
Right.
Well,
Correct.
good thing we didn't come in at 1 then.
Yeah.
We were
Right.
late.
Yep. So if you go to the registrar side, there's a course schedule for exam. You can find our time period. It's there. And there's a set of study problems, and I'll post some solutions, over the next day or so. For those.
Okay. Thank you. I just wanted to make sure.
Sure.
I know some professors say, well, actually, I want it at this time. And I didn't.
Yeah, no, it's it's hazardous to change that with everybody's interrelated schedule. So hopefully they've chosen these so that you can't have another, Monday, Wednesday, Friday class, and taking a second class at the same time. So we won't conflict.
Is there going to be any more like class material before the exam, or?
Nope, no, nothing else new. We're going to look at an article that uses examples of things, and then just do a review go over some of these study problems and questions on Wednesday.
Could we?
So for this one, you can have 2 pages of notes, right? So before you had 1 page of notes, you can reuse those same pages of notes if you want to, or you can specialize. Now we're not putting quite as much on the exam, and not all particular topics, so you can specialize it.
So is it mostly focused on stuff we've seen since the last exam, or kind of even?
The things that, the confidence interval things and hypothesis test for 2 proportions, a lot of that was on the previous one, but these kind of couple specific things. This one, the 2 proportions, was actually after that one, but certainly a confidence interval just for a single mean was there before. Right? The other thing that was earlier is just these normal probability calculations. Came a little bit earlier, it was on an earlier exam. The one other thing, just to complete this list, is conditional probability. Kind of probability trees. I like those. I think they're useful for thinking about chances and comparing groups and doing that showed up on exam 1, the 3rd problem. So it would be similar to that. So the normal, the conditional probability, and the confidence interval for what mean is kind of the older material. Now, within the context of all this is a little bit of interpretation, right? So if it's a significant result, but you think there might be a bias in the study, or they didn't use randomization, you know, then it's hard to conclude. You know.
So for the second exam, we went through and made like a nice little like formula short sheet thing for what was going to be on it. Could we possibly, one of the times this week, go back to
Some of that thing.
before the exam one stuff and get some of the
Yeah, so not so much, I mean, not too much from before exam one. would
well, like
be
not before,
on-
like exam one.
Yeah. We could ask about specific things if you have questions about details.
So
But you
it's-
won't get like a set of data and have to calculate the average or standard deviation.
Okay.
The average standard deviation would be given to you. You know, if it's a question about proportions, you might get a sample size and the number of individuals who are affected, so you can get the p-hat, the sample proportion out of that.
Okay.
But other formulas for confidence intervals, hypothesis test, we can kind of go over a little list,
Okay.
a few things now. Yeah.
So for exam one, it's only conditional probability?
So conditional probability, this is kind of the probability tree type thing, and figuring and Bayes theorem to kind of reverse that tree, the type of things we did with those.
So that's the only thing from exam one that's going to be on the
I wouldn't
final?
say, you know, that's the primary
Okay.
thing, you know, you won't have to compute a sample average or sample standard deviation. There could be a graph associated with some of these things, so if you get a significant result in, you know, for analysis of variance, well, it means that the means are different. So maybe the box plot you would see for comparison groups would look like there's some differences between the groups. So you might use a graphical thing, but it wouldn't be kind of in the context of that problem. Yeah.
What about like binomial probability?
You won't have any binomial probabilities. So there's enough as with the other material. So a little more detail on a couple of these things, right? So in analysis of variance, you know, say you have capital I different groups. There could be the averages of the different groups that you might look at. There could be graphs of the separate groups, maybe side-by-side box plot of the different groups. I might give you an ANOVA table. I don't plan to have you do a lot of manual computations, like here's 3 means and some standard deviations, and you know, you get more the table of things. Right? For the table, you might fill in some values of the style, you know, that a mean square is the sum of squares divided by its degrees of freedom, or the F statistic is a mean square treatment over a mean square error is a ratio of F. So a few things like that might be filled in. Degrees of freedom is I minus 1 for groups. There's 1 minus and less than the number of groups. And then there's n minus I, the number of the sample size, total sample size minus the number of groups for the error. So there's a couple of things in there that can be filled in without a lot of computation.
What's the SS again?
Sum of squares. So there's usually degree of freedom column, sum of squares, mean square, and then F. Right? Say hypothesis, or hypotheses. The means are the same versus the means not being. Based on the ANOVA table, that would have a p-value. You have a conclusion about hypotheses. And the hypotheses concern the means, so you could phrase it. The means out of the ANOVA table, we also get an estimate of the variance of the measurements, standard deviation of measurements. There was take the square root of the mean square error from the table, you get that. might use that to make a confidence interval for a mean or a difference of mean.
So that's, so that is the variance then?
Yep.
Okay.
First, estimate of the standard deviation there. And so if we wanted, say, a confidence interval for a mean, or say one of the means, we have X bar, the sample in that group, plus or minus a t-value. We use that upper cutoff level, but then there's n minus I. We can use the degrees of freedom for the error instead of just that one group. Not n sub I minus 1, but the big one there, and there's a sigma half, and that divided by the square root of n sub I. So that would give us a confidence interval for one of the groups in this ANOVA framework.
And the 0.975 comes from just their confidence? or-
Yep, confidence level. We'll use 95% confidence levels for everything. And that is the cutoff there.
So are we gonna, would we have to calculate things like the mean square error and the,
That would come from the table. That would be involved in that.
so for mean square error, how would you do that one?
Well, we could maybe look at an example.
Yeah, that would
right?
be great, thank you.
Right. So the example, earlier in the year, we had some data on streams from Professor McCabe about species that were observed there. And this is two others, two from psychology, right? Professor Richardson and David Tate Manculo, right, did this journal, right, article. So they have participants in a laboratory. Some individuals are exposed to this something called a star mirror tracking test. So they get some test where they have to do this kind of stressful thing on the computer. And the others are relaxing, watching a nature video and being relaxed. All subjects before this were not supposed to engage in any really stressful activity the day before, kind of go relaxed into this. They had some restrictions about how much, when they were eating, so there's, and so on. And then they performed 2 spatial tasks. In the first task, they have to navigate through a virtual reality environment, and then they make some other judgments. And the second one, a perspective-taking task. They have to make directional judgments, targets like how far and so on. So things that require judgment and thinking and are not just necessarily the quickest decisions. They have some hypotheses about how stress affects the nervous system and our ability to reason and pay attention and think about things. Right? And so in this, they measured a bunch of things. So what would you measure in this? Studies like this measure a lot of things. Heart rate, systolic, diastolic blood pressure. You have one group having a higher heart rate during these activities versus the other. They measured, they had a questionnaire that asked about being anxious, angry, frustrated, irritated, and things like that. People would score their feelings, right? People that were exposed to that stress had more negative emotions according to their scales. They also measured salivary cortisol. And so in the psychology, the different things they're measuring are related to different biological processes that affect mood and affect behavior and so on. So they're not just random things, they tie them into different parts of the body and different things like that. And they had males and females. So in an article like this, they would go through a number of things, so some background of what's going on. They have participants who are randomly assigned to either the stress condition, 10 men and 11 women, or the non-stress condition, 12 men and 14 women, about balance between the two groups. They were randomized. They tested between 8 and 11 a.m. People were supposed to abstain from alcohol, caffeine, and physical activity for 12 hours before that, try to put their body in a more neutral, right, relaxed stage, right, informed consent, right, ongoing, monitoring of blood pressure, and so on, and then they were. They sat and listened to quiet music to relax, and then one group got this stressful star, mirror, trace task, and the other ones had this other thing. Immediately following that, they went into the different things, and they tracked how long it took them to do that, their accuracy, and all these other measurements. And the article describes more about the 47 non-smokers that were in the study, about how they measured everything, little pictures of some of the virtual reality test, and then as this goes down, data reduction and analysis, ongoing monitoring of blood pressure, heart rate, but they want to get it down to a few more precise measurements. All right, kind of a little something they had to describe in terms of that. And out of this, what they report is they're doing something called a mixed model analysis of variance. This is one step beyond what we've done in the class, but the so the 2 and 2 is there are stress, no stress, right, as groups. And there's also men and women. Previous research has justified that there may be some difference in some types of perceptions or response to stress. That's one variable they record and keep track of. The 4 is in there because they measure the same people at baseline during the stress, no stress interaction. And there's this virtual reality and this pattern task. So they have multiple measures on each one, and this kind of mixed mode ANOVA has a random effect for each person that kind of adjusts for people's differences beyond this. Right? So they have F statistics, p-values for reporting different significance things. We're not going to concentrate too much on that. They get nice graphs, heart rate, baseline during the stressor period or the video period, and then the 2 tasks. You can kind of see differences. There's the black box in this. You're kind of making confidence intervals about these. This one, confidence intervals look different. These confidence intervals look like they overlap quite a bit in there. So heart rate, systolic blood pressure during the stress, it definitely produced a big difference there, and then it seems to persist a little bit afterward, right? Other blood pressure. Then they have other things like salivary cortisol, baseline to post there. They report averages, means, standard deviations between these different things. And for instance, if we look at a table like this, at baseline they did these questionnaires, and people got a score. How frustrated or angry or so on are you? And so there's a stress, non-stress, non-stress, and then stress, averages, and standard deviations. And that would be information we can use to make confidence intervals or do ANOVA and things like that. So let's look at a little bit of the data. In particular, we could look at some things that we would do for analysis of variance. So in the data itself, there's a lot of different variables that get reported in the data set. Right, for something like this, they ask a lot of things that are, cortisol, they take the difference of that, the log of it, height, weight, BMI, report time of day. They've asked them a bunch of questions about what they do, kind of on a regular basis, to find out that might be related to their that. And then during these different things, like the virtual reality, what errors they make. Yeah.
What does hold toothbrush measure?
They had something about
right there.
Yeah, hold toothbrush.
It says hold toothbrush.
Right. And so they're trying to determine which hand is the dominant hand.
Oh, okay.
Something like that. Right.
I just.
Because they're going to.
You were just scrolling, I saw hold toothbrush.
Yeah, and so I would guess
very
that's
relevant. Yes.
you know, they do mention that they put the blood pressure cuff on the non-dominant hand
Oh.
for each person, and maybe there's a difference in, you know, how things go, yeah, but, right, so how's it, hold toothbrush, right, hold a knife, I don't know what the code is, but toothbrush, yeah, I don't know what it, 1, 3, 4, and 5 mean, but there's some reason they wanted to know that, right? So maybe it's only one hand, or maybe sometimes, you know, something like that. There was like a numerical scale from 1 to 5. If right hand is dominant, for most people, maybe 39 people said they only hold it with their right hand. But then others said some left-handed and some either one, you know. Let's look at some of the analyses as I put them in there. So one is, do you take prescription drugs? Right, was one thing in there. Does that differ by gender? Well, of the 22, I think 1 is male and men, and 2 is women. I think they did it alphabetically that way, so the 22 men and 25 women are in the study. You get these different rates. Let me see. So one part of that could be, you know, one part of our test, I said, would be 2 proportions. We'll come back to ANOVA as we get to it through this list, right? So in terms of taking some prescription drugs, there's males and females. And we have this 2-way table out of that. You know, yes or no were the two responses. Out of the 22 men, you got 3. So the rate for the men was 3 out of 22, or 16%. Whereas for women, it was 12 out of 23. And so the rate for women, 12 out of 25, is much higher, 0.48. 0.48, yeah, there. And we could ask, is the rate of taking prescription drugs the same in the 2 groups? We could do a hypothesis test. Is the rate of prescription drugs the same in the men and women? Versus an alternative that these are not. Now the women ask, why is it so much higher? Maybe this includes birth control drugs, maybe some drugs for a certain, I don't know. That would be the thing that comes to my mind in this population that would make things so different, right, in terms of rate. It's not asking about why you're taking the drugs exactly, so see that there's some difference and not know why. So the hypothesis test, we would, the overall rate of this across all groups, there's 15 out of the 47 in all, so that's 32 there, so 15 out of 47. So to test this hypothesis, we would get a z-statistic. We take a difference in these 2 rates and divide by a standard error. We have the p hat, 1 minus p hat for the kind of the variance part, and then we have the 2 sample sizes. 1 over number for the women, square root of that. And so 0.16 minus 0.48, and that's, do I have that one overall? You know, I don't have it overall. I did some calculations, but I didn't do exactly what I needed. So the 15 out of 47 is what? It's 15 out of 47 is 0.32, right? So 15 out of, this is 0.32. So this one is going to be 0.32, 0.68, and then the 2 sample sizes, 1 out of 22 and 1 out of 25. So if you calculate that we could see if that is significant or not. I do this, so I do my calculation here and make this kind of right. So 0.16 minus 0.48 divided by the square root of 0.32 times 0.68 times 1 over 22, 1 over 25. Ends up being negative 2.35. As a z-value, what's the probability that a standard normal is less than negative 0.235? It's pretty small, right? So it's going to be less than 5%, less than 2.5%. The chance that a standard normal is less than negative 2.35, about 0.009. And so our p-value, we would double that, 0.8. It's small, right, less than 0.05. So we would reject the null hypothesis. There seems to be a difference in this prescription drug, having prescription drugs between the men and women. So they might have done something in particular, because they would have been this different between men and women, maybe other ones. And the two treatment groups have basically kind of a very balanced number of men and women that are there. So that one's significant. In our class, we're not doing anything with this so-called chi-square test. It does, it's a different way of looking at that. For treatment drug by gender, right? Getting a small p-value, we're not going to do that. There's a, between the two groups, between those that are stressed and no stress, do they have a difference between prescription drugs or not? Right? You probably would hope that they wouldn't, right? Because they'd be randomized. Some men and women in both groups, roughly balanced. The p-value there ends up being not significant, and so we're not doing that chi-square part of it. Another thing we could look at is correlations of some of these variables, right? There are, fix the screen here. Blood pressure, so this is at baseline. There's heart rate, systolic blood pressure, diastolic blood pressure. Do any of those look related to one another? Right? Heart rate versus blood pressures. These two don't really particularly look so related. Right? They kind of look like random scatter. Systolic blood pressure, diastolic blood pressure, though, maybe we could even do a plot of B1 systolic blood pressure, B1 diastolic blood pressure. It's pretty random, right? But you can kind of imagine some kind of general trend going up there. Right? So regression, right? You might comment on this plot, right? As one question. If you run a regression, now this is probably something that'd be more correlated, right? Just because they kind of go together. And so, but if you regress one on the other, you might come up with this regression output. We'll focus, the type of parts that I might give you on an exam would be something like that highlighted part there. Right? So what's the, in this regression, what would be the estimated regression slope for predicting, in this case, systolic blood pressure from, so second type of problem, predict the baseline systolic blood pressure from diastolic blood pressure. What is the regression line get out of that regression, which is the bottom of the page 1 on the handout. So our y variable, our x variable. We saw on the plot between x and y, kind of a fairly loose but somewhat increasing, relationship. So we want to write down, based on this output, what is the intercept, right? And then the second coefficient is always the slope on there. So what it would look like, 45.3245 plus 0.9478 times diastolic blood pressure. And what do they say they recommended? What's a good level? It's 120/80 systolic blood pressure, diastolic blood pressure. Right? Some new recommendations say these could even be a little bit lower. Like I wish, right? You get that. But but that's about a 40-point difference between the upper and kind of the expanding and contracting blood pressure. And our intercept is about 45. It's about 40. It's about the difference between those two slightly. And there's there's not quite a one-to-one relationship with them going up higher. Right? If that was 1, then 1 unit increase in blood pressure, diastolic would say 1 increase in systolic, but they're not quite that strong. Not quite like that. Right? But that would be our prediction. So what if somebody if a person has diastolic blood pressure of 100, what is our prediction for systolic blood pressure? Use the equation to make a prediction. So if you have a diastolic of 100, right, it just means put the 100 into that one. So our predicted value is this 45.3. I would round it off a little bit. And 100 times that, 0.948 approximately times 100, right, 45.3 plus 94.8. It's going to give us a prediction of 1, and that's 5, 0. Carrying another 1 is 140. So diastolic blood pressure that's near 100, you're going to be predicted at 140, and that's kind of at the hypertensive range. That would probably suggest you would do something about it. Right? Medication or exercise or diet change, and see if you can't get down a little, reduce stress, and so on. Is there a statistically significant relationship? Or is the regression significant? Well, in regression, we usually test this hypothesis about the slope. Right? When people usually say, is it a significant regression, their meaning is the slope 0 versus not 0. And so if we have a hypothesis that the slope beta equals 0 versus an alternative that the slope beta is not equal to 0, in the output, it gives an estimate, standard error, t-value, p-value, along there. So our key statistic would be our slope over the standard error to 0.9478 over 0.2388 and 3.97 approximately. So a statistic that's 4 standard errors away practically. Long way from 0. Degrees of freedom, n-2. Now in the output, if you look on the top of the second page, it says 9 observations were deleted due to missing it. They're either missing systolic blood pressure or systolic or diastolic blood pressure. They're missing one or both of those. In this study, they took multiple measurements. There's actually a second measurement taken, so maybe if the first reading didn't work out, they took a second reading. they're doing it with these automatic cuffs. And so it doesn't mean that the people didn't have data they could use, but in terms of this, there might be some missing data, right? So it uses, it's supposed to be a -2. It uses 36. There must be 38 with both, X and Y observed. Even though there are more in the study, there's some that aren't used for this analysis. So if you wanted to compare this value, we would look up the 0.975 value with the appropriate degrees of freedom. So using 36 in this case, the cutoff value, right? I'll give you a t-table and a normal table. I don't have them open here today, but the t statistic on 975 degrees of 97.5 percentile for that 36 one is 2.03. So if you wanted to look up that value, you would find a number like 2.03. And because our statistic is so much bigger, we reject. What percent of variability is explained? Not much. Not much, right? So percent variability explained. That's that R squared statistic. And so it's called multiple R squared here. It's about 30%. So it's something. It's not 10% or something. So it's still part of it. Right? There still is a trend there, kind of going up, even though it's weak. So that's regression would be asked kind of in those ways. What else is there? VR, right, was another time period. That's after the virtual reality interaction. How does the two blood pressures relate there? Well, here's the pairs of heart rate versus these. This one looks a little bit stronger response here, I suppose. So if you plotted just the VR1 systolic blood pressure, VRR1 diastolic blood pressure, those perhaps show a little stronger relationship. When you regress those, you get very similar coefficients, 45.947. This is that R squared there. That's the R squared for this one. Maybe the base one is not quite as strong. Maybe I got, so B1 systolic blood pressure, B1 diastolic blood pressure, that systolic blood pressure, diastolic, oh right, blood pressure. Oh, that was just 0.12. So the base one that we were talking about, that picture, right? That this base picture is only about 12% R squared. But the one with after the virtual reality, once the stimulus is there, then the correlation was a little bit stronger, 0.33. Right. There's this cortisol. They took the log of the cortisols. You could look at cortisol related to heart rate. That kind of looked positive. Cortisol related blood pressure. Those don't seem related, but the cortisol levels do seem to be related to heart rate. A couple of physical relationships seem related. So now getting back to this question about an ANOVA exam. The log cortisol, right? Why would they measure the log? Right, so a histogram of log cortisol at time period 1 looks like that. If they didn't take the logs, the inverse would be taking e to that power. It would be skewed. Right? So they've taken the logs of it to get it more normal, less skewed. Does the log cortisol at time period 1 versus stress versus no stress, how does that look? This is the cortisol at baseline. Does that look much different? No. That's a second measurement. Here's difference male versus female. This is taking the stress versus no stress and running an analysis of variance. So this is the picture. This first one is the picture. Right? This is group 1, stressed out, given the stressor and non-stress at the initial measurement. And here's analysis of variance table that comes out of that. Right, so here's the analysis of variance table that we'd be getting. Right? So what are the hypotheses we're studying in this case? ANOVA, we look at differences in means, right? So in this case, I can set this up a little bit more. ANOVA, so the Y is log cortisol measurement. And we have two groups. Those that have the stress applied early in the process and the ones that are not stressed. They're watching a relaxing video. Right, analysis of variance in test is the average value of Y, the same in the two groups. So same average value of Y versus an alternative that says they're not equal. And so there were, how many were stressed? There was n equals 21 in this case, and n equals 26 in this case. I, the number of groups, is 2. So if you have to fill out the ANOVA table, right, there's the different groups, which are defined in terms of the amount of stress experienced. Right. There's the error or residual in total. 2 groups. So this one, I minus 1 is 2 minus 1 is just 1 degree of freedom here. Error is n minus the number of groups, so 47 minus 2 is 45. If we had another row, R doesn't give that, it would be the n minus 1. So 47 minus 1 would give us 46. And the sum of squares, these things would be computed or given to you, right? So there's different ways of thinking about filling in a table. Now, likely I'll, to avoid having to copy an entire F table of multiple pages, give you the p-value for F, right, 0.87. With a large p-value like that, are you going to think these means are different or not? Or we're not going to, based on this, we don't need to know the rest really to get this conclusion. I do not reject H0. And as we saw in the pictures, these two groups, the salivary, the log cortisol, looks quite similar in those two. No real difference there. But if you're given part of the output, right, you could try and figure out some other pieces of it. So I keep taking the pages away. And so in this ANOVA output, right, so if you had, 36.28, then a mean square, that one's not as interesting. It's just 36.28 divided by 1, or still 36.28. We had the F value of 7.03. We could figure out that one. Right? Because that F has to be the ratio of the two mean squares. So the F, since it's 7.03, and this mean square treatment is 36.28. We could solve for the mean square error, right? So then the mean square error then has to be, that's 36.28 multiplied, put it up here, divide by 7.3, 7.03. That's about 5. The actual value is, from the table, 5.161, keeping all the decimal places. So if you had that part of the table, right, you could have 5.161. And once you have degrees of freedom and mean square, you can get the sum of squares in that row, right? Because the mean square is the sum of squares over its degrees of freedom. So if the sum of the mean square is 5.161, the degrees of freedom was 40, what was it, 45? 45. This means that the sum of squares is going to be 45 times that mean square, 5.16. So the sum of squares is 232. You multiply 232. You multiply that out. So some of the relationships in there, you just add or divide. So you get 232. You want to add those together. There's an 8, 6, 268 as a total sum of squares. So we wouldn't necessarily use too much more of that information. But anyway, there does not appear to be a significant difference between those things. How about, though, there was another outcome variable in there, y is time for pattern tracking task. So one group is stressed, another group has not been stressed. They did the virtual reality, and then they're doing this pattern tracking. It was a randomized study, so other than that treatment, the different experience there, they should be the same. So the stress group, which had 21 versus the no stress group, 25. What does it look like if we look at that variable in terms of ANOVA? Here's what that variable looks like. PT, RT is the name of the variable, kind of the time in minutes to do this activity. Here's the box plot comparing the groups. Does this one look like there's going to be a significant difference between these groups? Right? So one is the stressed group. What impact does stress seem to have on the time to complete this? Suggests that I think that part of their conclusion is that that many things are the same, but some things are different. So even if you don't see changes in heart rate or things, there's still some measurement, like the time to do it seems to be significantly different. And it's not all because of outliers, right? There are maybe one or a couple outliers in each group, but the group is really shifted down. So if you do an analysis of variance comparing these two groups, right, you get this table. Degrees of freedom are the same. Sum of squares, of course, are different, totally different measurement scale. We get an F value of 7, and then a P value of about 0.01. So for this picture, the ANOVA corresponds to a significantly different, in means. So if we got this, we could ask, well, what is the difference in means? How different are these on average? Right? This 5.161 here is the square of our estimate, 5.161. So our sigma hat is the square root of that thing, your root mean square error. So the square root of 5.161 is that. The averages of the two groups are 7.31 and 5.55. There's 21 in one group, 26 in the other. If we have 45 degrees of freedom, like we do here for this response, the 97.5 value for that t distribution is 2.014. And based on that, we could do a confidence interval for the difference between these two groups. So we're doing a confidence interval, 95% confidence interval for the difference of these groups. And the time for the first, funny. The average difference is, x bar 1 minus x bar 2 plus or minus a t value, and then there's sigma hat 1 over n1 plus 1 over n2. And these numbers are 7.32 minus 5.55 plus or minus, and what we looked up there would be the 2.01 cutoff value, or 2.14. And this sigma is the square root of that thing. So I compute that, 2.27. So this is 2.27. And then we have 21 in one group and 26 in the other. And that's going to be our 95% confidence interval for the differences. And that's all going to be positive. They're significantly different, so the interval is not going to include 0. But that would be the average difference. This difference here is if you had 1.77, I believe, minutes is the average difference between the groups. So there'd be a confidence interval plus or minus on that for some period of time. So that would be an example of ANOVA. Right? You do the table, some graphs, fill in maybe parts of the table, do some other, do a confidence interval or hypothesis test. So regression, ANOVA, proportions, something about the control charts, normal probabilities, and there's a couple examples on the study problems of the trees, conditional probability. So kind of focused on those things out of the class. But any other questions about things? What does the article conclude out of this? Right. So it has some differences there, and so so then there's some discussion. Does that be done? It was too big for me to read. See what's going on. So they contributes to our understanding of the influence of spatial stressors on spatial performance. Right? Acute stress resulted in similar accuracy but slower performance in two spatial tasks, which may be due to the increases in the negative effect. And that's what those questionnaires about anxiety and anger and irritability and things like that, things connected to these measurements of psychological performance, and so on. Anyway, and they had some individuals who helped them with who very well might have been St. Michael students, I'm not sure, helped them with some of the data entry. Right? But anyway, any questions? you can imagine the time it would take to do an article like this. Besides having the background to set things up, the article was submitted in 2010, got reviews, comments back, they revised it during that next, the comments probably came back from them, 2 to 3, 4 months later. Spent 2 or 3 months revising it, checking things out, resubmitted, and then it was accepted pretty shortly after that based on the reviews. And probably, it looks like it was printed later that year, maybe 5 or 6 months later that year. But the study probably was done the previous year. And planning for that was probably done the year before that. So there's probably a couple years before they get to the first submission, and then another year and a half or so. So it was a big effort to do these, and the statistics played some part. But certainly the psychology background and the theories, motivated the hypotheses, and the statistics then becomes a useful tool for establishing some of the results. So on Wednesday, we'll go through, if you bring questions about homeworks in the past or problems, we'll look at the problems that are posted. I'll give solutions before those, but it'll also be time for just general questions. Good. Yes.
I'm still waiting for the person I asked to give me the data to give me the data for the project.
Okay.
And I'm getting a bit nervous, so I'm questioning where would you suggest another source for statistical for the project might be? Actually get that sort of data to be able to do the project.
And remind me again, what type of data was it going to be again?
It was going to be environmental data on rain or the diffusion of immunolabeling in spider braids, basically. And I asked the person if you a little while ago, and I still haven't heard anything back. And I'm like, there's 2 days left. I don't want to be left with nothing.
Let me think about it. Maybe I can send you something later.
Even if it's just as a backup sort of plan.
Yep. All right.
Since once I have the data, it shouldn't get too long for me to actually do the analysis.
Right.
It's just I don't want to.
Yeah, and so it might be based on that. It might be a summary article with some statistics in it, in which you could do some descriptions of things out of that, or repeat some of that. But yeah, I'll make a note and then try to send you something.
Yeah, and I'm still chipping away at the homework. It's just been a really rough week.
Yeah.
My boyfriend broke up with me also on Thursday before. It's nothing's going on.
No, it's not your semester.
It's not my semester. I swear to God. If you got me 2 semesters ago, it would have been an entirely different story. But all right, I will get it done though.
Let me make a note, and then Jenny, you have a question? Tell me.
Thank you.
I was just sketch of the graphic.
So this is time period in here, so this is going over time.
It was labeled 1 colon.
Yeah, so there were 22 time periods in there. And so in R, this produces the numbers 1, 2, 3, up to 22 in there. So there's 22 different samples over time. And this sum thing is looking at, this is the deviation of the first X bar from that. And it adds the second deviation and the third deviation. And
So it said, I think in my book or something, it's supposed to fluctuate around 0, but this doesn't. This means it's
yeah, something's slipping out of control.
Okay, cool.
Yeah.
Hey, Kelly, are you going to senior week?
Yes.
Can I send your office
I'm sure
text
you'll do
after
it.
9 to 10 to
Yep.
ask questions about R/make sure I'm going
Okay.
away with the project?
Yeah, that'd be fine.
They
Yeah.
graduating are gonna actually participate in senior week, but some of them might not be, so I may not even, I'm not gonna volunteer and be gone all day if they're not gonna be.
Yeah, I see.
So I'm waiting to find out. I had a question about the project again,
Yes.
so I'm confused again because, so my hypothesis was that motorcycles are becoming more dangerous,
Mm-hmm.
and then my alternative was